Welcome to the TOEFL listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor, or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good morning, Professor Patel. Thank you for meeting with me during office hours about my project on algorithm selection.
Good morning, Mark. Tell me about the data set and the prediction tasks so I can help you choose appropriate algorithms.
I have two related tasks. One is predicting equipment failure from multivariate sensor time series. The other is detecting fraudulent transactions in tabular data with many categorical features.
Those are useful examples to discuss. For time series sensor data, think about models that capture temporal dependencies and handle continuous inputs.
Would a recurrent neural network be the choice then? Or should I use classical methods like hidden Markov models or autoregressive models?
It depends on the amount of labeled data and compute budget. If you have a large labeled data set and GPU access, deep models such as recurrent neural networks or temporal convolution networks can be effective.
What if the labeled data is limited, and I need interpretable results for engineers to act on maintenance alerts?
In that case, consider feature-based approaches combined with classical models. Time domain statistics plus tree-based models or logistic regression can be more robust and interpretable.
So interpretability is a selection criterion along with data size.
Exactly. Algorithm selection should weigh data characteristics, task goals, and constraints. For instance, for tabular fraud detection, gradient boosting often performs very well with mixed categorical and numerical features.
You mean methods like XGBoost and LightGBM are preferred for tabular data?
Yes, gradient boosting handles heterogeneous features, is robust to missing values with proper handling, and tends to capture nonlinearities without extensive feature engineering.
What about support vector machines and kernel methods for tabular data?
Support vector machines are useful for small to medium-sized data sets and for high-dimensional spaces when you need a clear margin-based classifier. They become costly on very large data sets, though.
And for high-dimensional sparse text like sentiment analysis, would naive Bayes still be sensible?
For bag of words and sparse representations, naive Bayes is a strong baseline because it is simple and fast. Transform models such as logistic regression or linear SVM with appropriate regularization also work well.
You mentioned regularization. How does regularization influence algorithm selection?
Regularization is a tool to control overfitting. If your features outnumber samples, you want models that provide shrinkage or feature selection, such as L1, regularized logistic regression, or tree-based models with built-in feature importance.
What about ensembles and stacking? They seem to improve performance commonly.
Ensembles like random forests and gradient boosting reduce variance and often improve generalization. Stacking multiple model families can yield gains, but increases complexity and reduces transparency.
So there is a trade-off between predictive power and interpretability.
Correct. If stakeholders need explanations, you might favor a simpler model or use interpretable surrogates and explainability techniques for complex models.
How should I handle imbalanced classes in fraud detection and failure prediction when selecting algorithms?
Class imbalance affects both model selection and evaluation. Use metrics such as precision recall or area under the precision recall curve. Some algorithms allow class weighting, and others require sampling strategies before training.
Are there algorithms that handle imbalance better out of the box?
Tree-based methods and gradient boosting can accept class weights and are more robust, while probabilistic models can be calibrated for class imbalance.
I am also worried about hyperparameter tuning. What is a robust approach for model selection and tuning?
Use nested cross-validation when you need an unbiased estimate of generalization and proper hyperparameter selection. That way, the inner loop tunes parameters and the outer loop estimates performance.
Does nested cross-validation apply to deep learning as well if I am tuning learning rates and architecture?
Yes, but it can be computationally expensive for deep models. In practice, combine a validation set for architecture search and cross-validation for final assessment when compute resources allow.
Could you give a concise decision guideline for selecting algorithms based on data type and priorities?
For images, choose convolutional neural networks if data quantity is adequate. For sequential data, choose RNNs or temporal convolution networks with enough labeled sequences. For tabular data, try gradient boosting, random forests, or regularized linear models. For sparse text, start with naive Bayes or linear models. For small data, prioritize simple models and feature engineering.
Are there computational constraints to consider beyond training time?
Yes, inference latency, memory footprint, and the need for real-time prediction matter. K-nearest neighbors, for example, is cheap to train, but expensive at inference if the dataset is large.
I see. For my project, I think I will prototype with gradient boosting for the tabular task, and start with feature-based trees for the time series, before trying deep temporal models.
That is a sensible plan. Remember to document your selection rationale and report metrics appropriate for your objectives and class balance.
One last question. If I have limited labeled examples but many unlabeled ones, what selection strategy would you recommend?
Consider semi-supervised approaches or self-supervised pre-training to leverage unlabeled data. After pre-training, you can fine-tune with a simpler supervised head if interpretability is required.
Thank you. This discussion clarified how to map data types and project goals to algorithms and evaluation strategies.
You are welcome. Send me your experiment plan and we will review the results and next steps.
Listen again to part of the conversation. Then answer the question.
If your dataset is small and you need interpretability, choose logistic regression or decision trees with regularization rather than deep networks.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit Spinta.org.